Hello. Well, last time we did the second half of bases, and we represented vectors with respect to bases, so naturally the check-in asks us to represent some vectors with respect to bases. So here we have two different bases, b1 and b2, and we're going to represent a single vector, v, with respect to those two bases. So let's get to it here. Okay, so let's see. I'm trying to represent 1 minus 2x minus 2x squared. 1 minus 2x minus 2x squared. I'm trying to represent it with respect to that first basis, so I'm looking at c1 times the first basis element plus c2 times the second basis element plus c3 times the third basis element. So of course, I can absolutely write down a linear system. I find all the constant terms, they make an equation. I find all the coefficients of x, they make an equation. I find all the coefficients of x squared, they make an equation. And I write those down. I get a linear system. Gauss's method will solve it. And you can always fall back on that. But nobody made it a crime to be smart enough to spot a pattern, even if it's slightly different from the pattern that you've looked at in previous cases. And in this case here, you see that on the left-hand side, there's only one term involving x squared. On the right-hand side, there's only one term involving x squared. So from that, I conclude that c3 is minus 2. Nobody made it a crime to be smart. Not yet, anyway. So now, likewise with the x's. On the right-hand side, there's only one term involving x's. On the left-hand side, there's only one term involving x's, so c2 is minus 2. Taking those two together, if c2 is minus 2 and c3 is minus 2, the constants give you minus 2 and minus 2 plus c1 equals 1, so I conclude c1 is 5. And that gives me the representation. The representation with respect to the basis b1 of the polynomial is, you got to write them in the correct order here, 5. 5 comes first, and minus 2, and minus 2. Notice that I'm calling it a vector and writing it as a vector, even though it's a polynomial, because it's a member of a vector space. This is a member of a vector space, perfectly fair, so I can write it as a vector. Okay. Second question asks me much the same thing. 1 minus 2x minus 2x squared. And I'm supposed to write that as somehow a combination of 1 plus x squared. C2 is times 1 plus x. And C3 times 1. And again, I could set it up and get Gauss's method. Set it up and get a linear system, and off I go with Gauss's method and get an answer. That's a fallback. Works perfectly fine. Absolutely perfectly right. But in this particular case, I can see by looking at both sides of the equation that the only time x squared appears on the right is as c1 times. The only time x squared appears on the left is as minus 2. So I get that c1 is minus 2. If c1 is minus 2 and I compare the x's, then I'm looking on the left at minus 2 c1, minus 2x, and then plus c2. So I get the c2 is 0. So again, absolutely nothing wrong with Gauss's method. Gauss's method would come to the same conclusions, but there's also nothing wrong with having a little brain power, having a little brain power and figuring it out. Okay, so what does that give me for the constant terms? So I have c1 times 1 plus 0 plus c3 makes 1. Oh no, I said that wrong. So that's minus 2 times 1 plus 0 plus c3 makes 1, so c3 is 3. Okay, so again, to write the representation with respect to the basis b2 of v, it'll be different than this representation, but still be a representation. I've got to write it in the correct order, minus 2, 0, 3. You can absolutely write, for example, a subscript b2 if you're in a context where sometimes there's one basis and sometimes another, but we often, when we're working, often leave that off. They're just a question of laziness, just too many i's and j's, and a person starts to say, I'm just going to leave it off. Okay, so that brings me to talking about the talking about the material for the day. The title of this section is basis and dimension. So we've already done basis, so we must be about to do dimension. Oops, here we go, dimension. Okay, so the definition. A vector space is finite dimensional. Finite dimensional if it has a basis that with only finitely many vectors. So we've seen that a vector can have many different bases if one of them, it could be many of them, but if at least one of them has finitely many vectors, then you call the vector space finite dimensional. Just as an example, we've been working with R3, and R3 has a basis with 3 elements, the standard basis. We've also been working with the quadratic polynomials, and the quadratic polynomials has a basis with finitely many elements. Here's a quadratic polynomial, 1 plus 0x plus 0x squared. Here's another quadratic polynomial, 0 plus 1x plus 0x squared. Here's another quadratic polynomial, 0 plus 0x plus 1x squared. So this is 3 different quadratic polynomials, makes a basis for P2. So P2 is finite dimensional because it has at least one basis with finitely many elements, only finitely many elements. And then the vector space of 2 by 2 matrices here has a basis with 4 elements. I'm not going to check that it's a basis, but it's pretty easy to check that it's a basis. So that makes this a finite dimensional vector space. And in fact, the vector spaces that we've talked about have all been finite dimensional. You never noticed till now because I never needed the finite dimensionality until now. From this point on, we're going to restrict our attention to vector spaces that are finite dimensional. All the later examples and the theorems, everything assumes finite dimensional. You can work with infinite dimensional vector spaces. They're interesting and important, but we're just not going. You have to start somewhere, and finite is easier than infinite, so we're going to start with finite. What we're going to show is that for any finite dimensional space, all of the bases have the same number of elements. So here's an example. For the quadratic polynomials, here are 4 different bases, and I'm not checking that they're bases, but they're not. None of them is hard to check. This is the one I was just talking about a second ago, and here's ones from the check-in kind of stuff. Okay, so 4 different bases for the space of quadratic polynomials. They're all different. Sometimes they share elements, sometimes they don't. But every one of them has 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 elements. So although the bases are all different, they share a commonality. They share a number of elements. Likewise with the 2 by 2 matrices. Here's one basis for the 2 by 2 matrices. Here's another basis for the 2 by 2 matrices. They're different, very different, but they share the property that they both have 4 elements. Okay, so ready for the theorem that in a finite dimensional vector space, all bases have the same number of elements. And before I go on and talk about the theorem, there's a couple of comments I wanted to make. The first is that in some sense, this is the key result of the course. That this is the first sort of genuinely, perhaps unexpected fact about vector spaces. And so it's sort of the central thing that you absolutely must cover when you're talking about covering this course. That's the first thing. The second thing is the note that the proof in the book is different. This proof here relies a lot more on sort of I's and J's. The proof in the book is a little more abstract, a little more conceptual, and there are proofs in the exercises that are even more abstract, even more conceptual. In general, when you understand something in terms of I's and J's, you've proved something in terms of I's and J's. That's good. It's good to prove things. But if you can prove it a little more conceptually, that's better. And if you can prove it quite conceptually, that's quite good. I also think it's good to see something more than one way. So what I'm deliberately doing here, we don't do this very often, but what I'm deliberately doing is exposing you to 2 different proofs, the proof here and the proof in the book. Not because I'm dubious and so I need to prove it more than once, but because sometimes seeing it in more than one way is a help. And in particular, walking up that ladder of conceptual, walking from low level to higher level to higher level is a help. Okay, so I'm going to go through the proof. So you fix a vector space with at least one finite basis. So there may be more than one finite basis. Look at all those finite bases. One of them's got to have the least number of elements. I mean, if one of them has 6 and the other one has 7, then pick the 6. Okay, there it is. This is one of the bases that has the minimal size. I'm going to show that if you have any other basis with, it's got to have more than n members. Excuse me, if you have any other basis, it has to have the same number, n members. That it can't have more than n members. Now, because B is chosen to be minimal size, D can't be fewer than n members. That's what minimal means. What we're going to argue is that D can't be a basis and have more. That there's some impossibility about being a basis and also having more. All right, so I wrote D here as possibly having infinitely many elements. But I don't need infinitely many. It turns out, only going to need the first n plus 1. So the B has n elements. I'm only going to use the first n plus 1 elements of D. So the fact that it says dot, 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 and it looks like it could be infinite, I'm not going to need that. What I'm going to show is that from among those n plus 1 different vectors, there's a non-trivial linear relationship. That is to say, a1 delta 1 through a n plus 1 delta n plus 1 equals 0, where not all the coefficients are 0. And of course, a basis can't have such a thing. So it's not possible for a basis to have n plus 1 many different elements. All right, so that's the outline of the argument. Here we go. We set off. So the first thing you do is you take the deltas and you represent them with respect to B. B here, B. And when you represent the deltas with respect to B, you get some numbers, a C11 through Cn1, all, I don't know, 5, 3 halves, minus 7, sort of stuff, and all the way out to delta n plus 1, you get all these numbers. Okay, okay. The lemma that we saw at the end of the video last time says that the point of calling them representatives is that a relationship holds among the vectors if and only if the same relationship holds among the representatives. I'm interested in the relationship among the representatives because these are numbers. These, in principle, could be anything. They could be 2x2 matrices. They could be cubic polynomials. I don't know. But these are numbers, and so very good with numbers, so I'm comfortable there. So I've shifted over from talking about arbitrary vectors to talking about column vectors of numbers, of real numbers. You notice, right, you remember from the previous slide that these C's, all the C's are numbers. They're fixed. They're representatives. They're in the representation, they're coefficients of. They're in the representation of delta 1 through delta n plus 1, so they are just simply numbers. I'm looking to see whether it's possible to have A's to make this relationship true. Okay, so C's are fixed, the A's are variables. I'm looking at I'm looking at a linear system. It's a homogeneous system because those are zeros over there. Because it's a homogeneous system, it has to have at least one solution. You can't have no solution in a homogeneous system. So a person thinks, okay, well, there's either unique solution, in which case you get linear independence, or else there's infinitely many solutions, in which case you get linear dependence for the set capital D. Which is it? Well, there are n equations. You see them down there? That's an n. There are n plus 1 many variables. You see that? That's an n plus 1. The A's are unknowns. The C's are known. C's are real numbers. So there are n equations with n plus 1 many unknowns. Some variable, some A, does not lead a row. If you do Gauss's method on this, you get down to echelon form. Some A does not lead a row. There are infinitely many solutions. In particular, there's more than just the trivial solution. So there's a linear dependence among the members of capital D, so D isn't a basis. So back up to remind myself of the statement, in any finite dimensional vector space, all bases have the same number of elements. They can't have more than the minimal number. They all have the minimal number. Okay, so that gives me a definition for dimension. The dimension of a vector space is the number of vectors in any of its bases, and they all have the same number, so that definition is not ambiguous. In particular, where does the word dimension come from? Well, in the regular n-dimensional space, Rn, that's how many members are in the standard basis, so that's how many members are in any basis, so that's where the word dimension comes from. The quadratic polynomials has dimension 3 because I can name a basis that has 3 elements, and any basis has the same number of elements, so there I go. I'm looking at all of them have 3 elements. And in general, Pn has dimension n plus 1. The n by m matrices has dimension n times m, and it's easy to produce a basis that has that many elements. On to a sort of less obvious example. The solution set for this system is a vector space. If you solve the system, what you get is you parameterize, you get a basis with two vectors. There I go, a basis with two vectors. So the solution set for this system, I know it's a three equation, four unknown linear system, but the solution set for this system has size 2. So the solution set is a vector space of dimension 2. It's a plane. Because there are 4 letters here, this is a plane in R4, plane to the origin, in R4, spanned by those two vectors. Okay, a couple of results that the theorem that we just saw gives us sort of an immediate payoff. It gives us a number of results. So no linearly independent set can have a size greater than the dimension of the enclosing space. So if you have a 5-dimensional space, you can't get a linearly independent set of size 6. If you have a 4-dimensional space, you cannot get a linearly independent set of size 5 or 8 or 100. That is to say, reinforcing the intuition that we had earlier, linearly independent sets tend to be small. They like to be small. If you have a space of size 6, of dimension 6, a vector space of dimension 6, you could have a linearly independent set of size 6, you could have a linearly independent set of size 5, you could have a linearly independent set of size 4 or 3 or 2, but you can't have a linearly independent set of size 100. It just can't happen. And it's just simply, you examine the proof, and I never used anything about span, only linear independence. So the result actually proves this statement. Just as a remark in passing here, this statement is an example of what I said earlier, that we're going to take vector spaces to be finite dimensional without ever saying so. It doesn't say enclosing finite dimensional space, it just says enclosing space. I'm never going to mention that again. So if you give me a linearly independent set, I can expand it to make a basis by adding 1 element, 2 elements, 3 elements until I'm up to the size of the space. That is to say, I don't have to worry that I'd need to add infinitely many elements. Don't have to worry about that. Any linearly independent set in a finite dimensional vector space, any linearly independent set can be expanded and the process will stop. You add a new one to make the span bigger, you add a new one to make the span even bigger, add a new one to make, at some point you hit the dimension of the space, and at that point, guaranteed, it's not going to be necessary to add more elements to the basis because the basis isn't any bigger. And the flip of that is that any spanning set can be shrunk to a basis. Again, you don't need to worry there. You call the spanning set S. If S is empty, then S already has a basis. If S just consists of the 0 vector, then it can be shrunk to the empty basis without changing the span. The technicality is that the empty basis is linearly independent. So otherwise, S contains a vector that's non-zero, and we can form a basis that consists just of lowercase s. If the span of that linearly independent set is all of S, then we're done, and is all of S's span, then we're done. If not, then you just add a new one and add a new one. You'll never have to, because these are finite dimensional spaces, you'll never have to worry that you keep adding infinitely many things. After some finite time, this process stops, and all of the lowercase s's that you have not yet added in, you can throw away. Okay, so this idea that there's a limit to what you have to throw in, because there's a limit to what it takes to make up a basis, is key for both of these results. And then finally, in an n-dimensional space, a set composed of n vectors is linearly independent if and only if it spans the space. So if you have an n-dimensional space, and you have a linearly independent set with n vectors, you don't have to check span. Or in an n-dimensional space, if you have a set with n vectors, a spanning set with n vectors, you don't have to check independent. You get independent for free. Okay, and the proof is, so first we'll show that a subset with n vectors is linearly independent if and only if it's basis. The only if, the if part is trivial, the only if holds because a linearly independent set can be expanded to a basis, but a basis has n elements, so there isn't any expansion at all. So it must be that it was a basis to begin with. And then to finish, we'll show that a subset with n vectors spans the space if and only if it's a basis. Again, the if part is nothing. That a basis has to span. The only if part is because any spanning set can be shrunk to a basis, but a basis has n elements. And so if the shrunken set was, if the set you started with was n elements, that must be the set you're looking for. Okay, and so to look at this, we saw this earlier, to look at this particular subset of R3, I wrote it as a basis. I wrote the diamond brackets, which is we pretty much reserve for bases here. So I wrote it as a basis. If you glance at it, it's clear that it's 3 elements. That's clear. No matter how quickly you glance, it's clear that it has 3 elements. It's also clear that it spans the space. Because it has 3 elements, it must therefore be linearly independent. It must be a basis. Okay, so that finishes us and for the day. And what we're going to do next is we're going to talk about how the things that we have discovered so far apply to linear systems. We're going to take it around and tie it back to linear systems. Okay, look forward to that. Bye-bye.